Hi everyone, my name's Ryan Nienhuis. I'm a senior staff product manager at Databricks. I focus on streaming data. I'm going to be presenting today with my colleague, Praveen Katu. Little funny story before we get started. Praveen and I have worked together on streaming data with me, the product manager, him, the dev manager, for like 6 or 7 years. And I was going to give this talk with Karthik, but unfortunately Karthik couldn't make it last minute. So Praveen had 2.5 hours to prepare and present with me. I called in a favor after all these years. Just don't ask me not to prioritize the future, please.
All right.
All right.
So if I bomb, it's not on me, guys.
So with that, the talk that you're attending today, Project Lightspeed goes hyperspeed. It's the end of a long day. We've got some really, really cool announcements that we haven't really shared broadly yet that we're going to talk about today. Some of it will be talked about a little bit with the keynote tomorrow. And then we got some deep technical content that we'll cover with some of the new API functionality that we're releasing. So I'm really excited to get started. And here we go. So you're going to have to bear with me while I present my marketing slides. But the world operates in real time. And I pulled some 2 recent quotes from 2 recent analyses, IDC and Gartner. And I want to call out something very specific about this. Specifically for the Gartner slide, the quote says, "This information is most valuable when it's used as soon as it arrives and improved in real time." Today's talk, especially the front part of the talk, is about if you really want to get to data intelligence, some of the most impactful things you can do are with low latency in real time. And we're going to talk about some features that we're announcing today for you to implement these use cases faster, as well as a little bit more easily with some new API functionality. Great. So I think this is a more advanced talk, so I think most of you know this, but I'll go through it in a little bit more detail. So every company generates data in real time. The real question is whether they can capture it, process it, and derive insights it relatively quickly. All right? Data is constantly being generated from the programs you deploy on VMs, application logs, transactional records from databases, user behavior, click streams, that type of thing. So the key part about leveraging streaming data is making sure that you first can capture it, ingest it, hopefully into the lakehouse, and then also get the insights on it so that you can make an impact immediately. So it's one thing to generate a report, once a month or once a week, and those types of analyses are useful. Looking back, identifying trends, and those type of things, very, very important. But if you can, in your mobile app, detect that a user is not going to make a purchase and give them a notification or an offer, or if you can detect fraud in real time and stop a financial transaction that is clearly going to the wrong person, then you can really have an impact on your business. So Databricks leads streaming. And part of the reason why we lead streaming is, just 1 second. My slides are out of order, so I'm going to go on this one, because this is the most important one. The huge reason why we lead streaming is because we are based on OSS structured streaming. We've continued our investments in it this year. More than half the functionality we're presenting today contribute directly into open source. And structured streaming launched in 2016. And we've continued to innovate it over the past, 7 years or 8 years, where our innovation into the OSS is only accelerating. The reasons why we built structured streaming are still the same. We want a unified engine for batch and streaming. We want fault-tolerant, high-performance stream processing. I think the difference here is that the ease of use, as well as the performance you're getting now than it was 6 or 7 years ago, is tremendously different. And we are announcing some stuff today that takes that a step further. So bear with me while I go back to my out-of-order slides. All right, streaming is bigger at Databricks. We run millions of jobs per day, tens of millions of jobs per week on behalf of you. And this is across a lot of our products like Delta Live tables, it's including streaming jobs and workflows, both classes infrastructure as well as services infrastructure. And the cool thing about this graph, it's demonstrative of not just our growth, but also just streaming data's growth. You see the line is not, this goes all the way back to 19. The line is not, like growth is not slowing down. We're still in the early adoption phase of streaming. Customers are still just implementing their first 5, 10 critical use cases. And I believe 5, 10 years from now, we'll have customers with hundreds and hundreds and hundreds of streaming use cases, and that won't be atypical. At least according to an analyst, Databricks is the best choice. IDC MarketScape recently announced a report for stream processing. We're noted as a leader. What they told us mirrored a lot what our customers say. We have a really, really good development experience. It's easier to go from lower code to no code. We have good orchestration, deployment setup, and things like that. We're also offering an integrated experience. It's one of the things compared to the other people that are listed on this slide. You're not just going into some streaming data silo on this massive platform. Streaming data is everywhere. It's integrated everywhere in the Databricks Data Intelligence Platform. But, actually, one more point. Sorry. I ran into so many technology issues already. But we have a long way to go. And our customers, you guys, are the most critical of us. We have a lot of areas that we wanted to address. We've had hundreds of conversations over the last 2 or 3 years as part of what we call Project Lightspeed. Some of you might be familiar with this, but Project Lightspeed is like a marketing initiative, but it's also an internal call to action for us to accelerate the innovation we have with streaming data. We've launched over 30 features over the past 2 years, both in OSS as well as in the various Databricks products related to streaming data. Project Lightspeed, we're investing in 4 categories. One is performance and latency. There are 2 functionality areas we're investing. One is observability and ease of use and ease of operations. The other is API functionality. And the third is connectivity, making sure you can get data to and from your structured streaming apps, to and from the lakehouse. I'm just going to cherry pick some of the features that I have here, some of my favorite. Photon support for each batch. For each batch is a hugely popular operator, and it's super hard with all the complexity that customers do within that. To offer support for a very, very powerful performance feature like that was a pretty cool feature release that we had. The other one I like here is changelog checkpointing. Previously, the changelog checkpointing, when we back up state, if you're unfamiliar, the way we back up state in streaming is we store that locally and then we take a distributed checkpoint into cloud storage. Previously, we would store everything every single time. Now we only change just the records you've changed, allowing for a lot more efficient checkpointing, a lot more state for you to handle within your individual application. I think we're just getting started with Project Lightspeed. We have 4 cool things to walk you through today. First is we're going to cover one of my favorite use cases and the most common use cases, streaming ETL, and some new features we have related to serverless. The second, we have a brand new feature related to low latency operational processing that we'll cover. I'll briefly cover custom Python data sources, which is another OSS contribution. There's a longer talk that we have tomorrow that I invite you to attend to learn more about that. And the last thing is Praveen will take us home with probably the most interesting part of the talk, at least I think it is, the arbitrary stateful processing and some new APIs that we're releasing to OSS there. Probably some of the largest additions to APIs functionality that we've added to structured streaming for a long time. Great. So we're coming up on the Data and AI Summit. And we're trying to figure out how do we showcase all this cool stuff with streaming serverless that we're doing. So we decided to do a benchmark and highlight some critical performance features that we're adding to serverless and compare them to what other customers use on our platform or elsewhere in the streaming ecosystem. So I'm about to show some benchmark data that we have, and the comparison is Delta Live Table serverless. Honestly, the functionality for this particular use case is going to be very, very similar to jobs and workflow service. So the performance numbers you hear will be similar. Jobs compute for Spark structured streaming, so the most popular streaming offering on Databricks today. And then we looked at some alternatives and we tried to pick, we were debated doing like Spark on a open source, on a big cloud provider or Flink, and we chose Flink to just provide some more varied results. So Flink is another popular stream processing framework. We picked a major cloud provider, and we picked that as the other benchmark. The way the benchmark is set up, is pretty simple. We basically load a Kafka topic and then try to rip through the Kafka topic as quickly as we possibly can and load Delta as possible, as quickly as possibly can. It does some light transformations. The biggest transformation is honestly the persistence into Delta and the transformation into Delta, and then we run queries on that Delta table to see how performant they are. We measured 3 things. First, how quickly can we read through all the data in the Kafka topic in a happy case? How quickly can we read through all the data in the Kafka topic when we're killing nodes every couple minutes randomly? And what is the query performance after that data lands? So here I'm showing the results of, on the left to right, DLT with serverless, Databricks jobs compute, and Apache Flink with different settings running on a major cloud provider. And you can see that there's major performance improvements that we're getting when we're running on serverless. And it has to do with some features that I'll talk about a little bit later. But these are a modest improvement, all right? Definitely from Databricks compute. But where the real improvement comes is when you look at ingestion with failures. The specific parts of the serverless architecture, how quickly we're able to add new infrastructure, replace infrastructure, as well as how micro-batch architecture actually works allows us to recover from failures very quickly. So with all those randomly killing 2 nodes, you can see that the performance becomes a lot more drastic. And then what about read performance? What is the performance after the data lands on Delta? Because did we play any tricks or anything like that? We optimized on write, but we didn't optimize on read. The read performance is even starker for some use cases, up to 600% faster read performance with Databricks. Streaming ETL is a super common use case. Going from most common patterns are reading from a Kafka topic, writing to a Delta table, or going cloud storage to cloud storage. Typically, for every record in, unless you're doing deduplication, you're getting at least 1 record out. So there's no aggregation typically. One of the primary ways that we have to support the performance numbers I just showed you is a feature called stream pipelining. So stream pipelining does a really, really nice trick with the micro-batch architecture. What it does is it will schedule up to 5 micro-batches in the future as soon as a slot becomes available. So you schedule a bunch of tasks as part of your micro-batch. One of the tasks ends early, it starts scheduling the next micro-batch. And it does so while maintaining ordering and exactly one semantics, so you don't have to worry about that. Micro-batch, the stream pipelining feature works for both stateless and stateful workloads, all right? And you don't have to do anything to take advantage of it. Running on serverless, it just works. I've focused on throughput here and performance on throughput, but the other good thing is that it reduces latency. And one of the key ways it reduces latency, as you all know, with lots and lots of use cases, you could have a hot key, some laggard tasks. This allows you to do all of the work up front as much as you possibly can to help reduce that latency on the average. So it's available today in serverless. I would sign up for it, go test it out. If you're using job serverless and you want to go check that out, I'd highly recommend you use Python-based autoloader to do it using a trigger job. And for DLT serverless, your options are a little bit more varied with that. But we will be publishing a blog post on that with example code, example note worker code, and how to set it up so you can replicate the results soon. So we talked about streaming ETL, which is the most common streaming use case. There's another set of use cases that are more operational use cases, and depends on how you segment the streaming data use cases, but I typically like to think of them, they're either event processing, routing, filtering, delivery use cases, and then there's the real-time analytics use cases. But these operational use cases all have one thing in common. You're acting on the data immediately. So it's an event processing use case, you're triggering a rule update, you're running a bunch of business rules and you're updating a database. If it's a real-time analytics use case, maybe you're detecting fraud or something like that. So the power of operational use cases really comes in the fact that you're taking action immediately. So instead of kicking a user off your platform last time for like sharing their Netflix password or something like that. You're detecting it in real time and logging them out. In fact, that's a very, very common use case for the streaming video providers. Almost everybody implements it using streaming data technologies. If you're a manufacturer, or if you're in agriculture, or you're in health devices, and you've got very, very valuable assets, and you're trying to make sure that they're used in the most optimal way possible, don't you want to inform your operators, hey, you can make this adjustment, and then we can save some money, or their performance could improve here. And I think the one that's I think speaks to the most of us, the broadest set of use cases, basically doing like improving the user experience while they're on the critical path. So ingesting data, running some simple rule sets is also doing some analytics. You send a customer a email to go buy some boots. They start clicking on your website, clicking some shoes, and there's another piece of trending data that you're finding elsewhere on your platform. You start updating the recommendation and sending different emails. All right? This is where you start really unlocking business value. So today we're announcing real-time mode. This is a new mode with structured streaming that will give you millisecond latencies with data processing. The very, very simply, you basically just flip a switch and you use all of the existing operators that are available today in streaming. There aren't like changes to code that you have to make. Private preview is going to come in H2 2024. And to give you like a little sneak peek, and I know we'll talk about this in more detail as we get closer to private and public preview, but to give you a little sneak peek of how this works under the covers is basically we reserve capacity on the open slots, schedule a task, and then allow data to flow seamlessly from data sources through operators and your user code to data sinks without interruption. When results are computed, they are immediately sent downstream. There is no waiting on the microbatch to complete. That is the critical thing that changes with this new mode. So how fast is it? So our team's been working really, really hard, and these are early numbers that we wanted to show you as much to demonstrate what the stark differences in performance are. We're still going to be working on the performance and improving the user experience and things like that, giving you some control over like emission control and things like that. We wanted to share the early results that we have. So the P50 latencies is in the tens of milliseconds. The P99 latencies is around 100 to 200 milliseconds. We think the sweet spot will stop improving the sweet spot for performance and latency for us is probably around 100 milliseconds in the P99. So why am I talking about P99 latency? All right, I could give you the lowest number possible. The P99 latency is the most critical aspect for these real-time use cases. The reason being is because when you're slow on updating a dashboard, or you're slow on giving that user notification, you're putting that information on like business critical paths. The net impact of the slowest data is really bad. So you want to make sure that you not only can deliver fast latency, but you can do so consistently. The next question I asked, I went back and forth with our engineering team. I was like, all right, how did you actually measure this? Are you guys doing, like, is it a conservative estimate? Is it not a conservative estimate? These test results are set up on a Kafka to Kafka setup where we are taking basically the timestamps off Kafka's write-ahead log. So it includes the entire read time, the entire write commit time of Kafka in the end-to-end setup. It's a really, really conservative estimate. The goal here is like eventually you get so fast it's like it doesn't matter. That's the point of what we're trying to achieve with this, all right? We want to make the system latency of Databricks streaming immaterial to your use case. So you can spend all of the time that you need in resolving like a 10-second SLA or 15-second SLA or a 5-second SLA on these use cases, on your user code, on your logic, on the hops that you have to make to solve for the end-to-end solution. So the way we're thinking about these performance features that I just presented, the two that I just presented, over the long term is that both of these modes are super important. With microbatch mode, we can do these fun tricks like stream pipelining. We have higher availability characteristics because we're constantly scheduling tasks, as I noted with the ingestion duration. We'll continue to add features that meet the needs for the wide variety of use cases that microbatch solves. And the second thing that we're thinking about is real-time mode is really, really meant for when you want to make a trade-off on cost, because there is a trade-off, because we're reserving slot capacity and latency. You're able to do so and get as fast as you possibly can. The other point here is that on the Databricks Data Intelligence Platform, we're offering very catered performance characteristics to your specific use cases, all right, where you have to make very little or no changes to your code to take advantage of them, all right? Maybe some of them in the future we're able to automatically detect and just run one or the other based off it, but for now it's very simple, a flip of a switch where you automatically take advantage of it in the serverless infrastructure for stream pipelining and microbatch mode. Great. So private preview is going to start around Q4 2024. We hope to, GA timelines are a little bit, we hope to go GA probably earlier next year. The reason why is because we want to make sure that we support the wide variety of use cases you all implement on us with the latency that we're stating here today, all right? It's one thing for us to show a bunch of diverse use cases on stateless and stateful processing. It's another thing for it to make sure that it works with all the awesome and funky things you guys do with structured streaming. So this is my last topic, and then I'll get over to what I think is probably the coolest part of the talk, and it's a very short topic. Custom Python data sources and sinks. So this is a new OSS feature that is going to be released in Spark 4.0, but it'll be available in Databricks a little bit earlier. It's already committed to OSS. It allows you to build a custom data source and sink in Python. In the past, you were restricted to building these in Scala and Java using what's called the data source v2 APIs. That was one approach, all right, which doesn't really work if you're a Python developer, all right. Number two, you use something like for each batch or for each to write with some custom logic to get to a sink that you wanted to get to. That works. It's a super powerful operator. We love that operator because of how powerful it is. But the issue is, we can't always take advantage of all the features that we have when you're going into that space. In addition to that, that code is kind of hard to write. Making sure that when you're in that space, you have to maintain state consistency. You're responsible for exactly one's processing and maintaining those semantics. So we built this API such that you can build reusable connectors for both your own APIs as well as databases that you use that we don't fully support. This kind of goes on to our approach with the connectors in Lighthouse, where we are supporting, we're ever now expanding the number of integrations that we have. We added different support for Kinesis and Pulsar and PubSub over the time. But also giving you the flexibility to make sure that you can connect with what you want to yourself. There's a talk at the end of the slide. There's a talk tomorrow, a little bit later in the day, where Allison Wang, who's the engineer that was the tech lead on it, is going to give the talk. I'm doing a short intro, and it's basically her doing demos. It's a pretty cool talk. I highly encourage you guys to attend. And with that, I'm going to pass it off to Praveen to close us out. And also, thank you one more time, Praveen, for coming up. Here you go.
Thank you, Ryan. You guys are able to hear me okay? All right. Disclaimer, I had 4 hours to prepare for this presentation, so please bear with me, guys. Just a show of hands, how many of you guys have written stateful queries or heard of stateful streaming queries? Okay, we have a decent percentage of people who have done this. So just a quick primer, what is stateful queries? If you want to store the state of your query for a future use, that effectively means stateful queries. Or if your query stops and restarts, you want to have that state repopulated, that's called stateful queries. An example would be, I want to calculate the number of users that are visiting my website at a 5-minute window. That's considered as a stateful query. Or you want to deduplicate or dedupe your data that's coming in. generally considered a stateful query because trying to keep track of things. And structure streaming does provide that facility where you can locally store this data, we durably store that in an object storage, and which is all backed by a durable checkpoint that we maintain in the engine. There are two kinds of stateful operators that we provide in the engine. One is called predefined stateful operators. These are called aggregation operators like windows, sliding windows, tumble windows, or deduplication operators, or stream-to-stream join kind of operators. But not every logic is able to be defined by these predefined aggregators. You might want to build some kind of custom logic, which is complex enough that these predefined operators will not suffice. In that case, we do have these operators called flat map group with state and map group with state. This is how a flat map group with state operator looks like. It's effectively you provide a custom logic that runs as a UDF, and the state is provided to this custom operator as a group state operator. So you define in your, if you define in a flat map group with state operator on the data stream, and then you define your operation logic, and then the state is provided to you as a group state, and then the incoming rows as the parameters to the operator. Now, what's wrong with this, or what are the limitations, not wrong, limitations of this operator? There are a few limitations which restricts users on what they can do in structure streaming. One limitation is this particular operator does not allow for ability for customers to use or store composite types like list state or a list, a map. These kinds of things are not allowed in the flat map group with state. So as a result, if you want to append a value or you want to delete a value, this would involve you to read the entire state, manipulate, and then store it back, which is cumbersome, less not efficient, but that's the limitation that is there. The second is, as you saw in the previous slide, the entire state comes as a single data object, which means if you want to model your state, you don't want to just store one entry, you might want to store multiple entries. You cannot really model them flexibly. There is no granular eviction of state. Schema cannot be evolved of the state. So if a state, you have like 3 or 4 columns and you want to add one more, that's not allowed today when you use flat map group with state. So what is needed is a way for you to have like a flexible, extensible stateful operator. We are glad to introduce a new stateful operator called transformWithState. This particular operator is actually, we are developing this in open source. The Scala API part of this operator is already checked into open source. If you're interested, please do take a look at that. So the way we have built this operator is a layered approach. We have introduced a state processor API, which takes advantage of the mechanics of composite types, state timers, metadata of a state, and then that layers into the state store provider. By structuring it like this, in future, we can add new state operators to take advantage of all these fundamental building blocks. So how does this new state API looks like? For me to talk through these next 2 slides, I'm going to take an example of a credit card transaction, like a fraud detection kind of a use case. So let's assume you are building a fraud detection use case. And so now you can express your transformWithState API on your data frame. And then to the transformWithState API, you're going to pass a new state processor API, which is called fraud, in this case, is called fraud detection processor. How does the fraud detection processor looks like? So you can express it effectively has 2 APIs. Init, you need to have an init method, and then you have a handle input rows method. So you can express your state, like over here, which is as a case class, and you can store that state here as a list state. You can also choose to state, for example, say max transaction value. because I want to compare against this max transaction value. And for example, if an incoming transaction is more than a certain threshold, I want to flag it as a fraudulent transaction, potentially. That's what I want to do potentially. So these are the two state things I want to store in the state store. As a result, when the handle input rows is called, whenever the new input is coming in, the transactions are given to you as input rows, and then you can use that input rows to compare against the state that has been pre-populated for you in the init method, and then you can take action. So what this allows for you here is you can model your state as, like if you're familiar with object-oriented concepts, you can model your state as such, and then that allows for flexible operations. And it's also optimized. So a big thing that I want to call out is like the second bullet point over here. When we do this init action in the init method, where we load the transactions and the max transaction, these are very lazily loaded. So if let's say you're not going to use those things in the handle input rows, these are never read from the disk. But if you're reading only that part of we take advantage of advanced concepts in RocksDB, like range scans, to only load that part of the state. So you're very efficiently making changes. So this is going to be much, much more performant than the existing state operators. It's not just this. We are also introducing timers to this state. So you can express timers, and then you can, when those timers get called, you can take certain actions. You can have things like these timers are durably stored in the checkpoint. The timers are deduped, and you can also express multiple timers to the same grouping key. Lot of flexibility for you guys. Another interesting functionality that we're going to provide with transformWithState is, a year ago, we have introduced this concept of ability to chain multiple stateful operators. But in that feature, we did not support flat map group with state due to certain underlying fundamental limitations. But the new transformWithState operator is going to be supported with such that you can chain multiple stateful operators, such that an output from one can be an input for the other. This can be super useful. For example, if you're calculating a 5-minute window and a 10-minute window, you don't want to recalculate again for the 10-minute window. The input from 5-minute can go into the 10-minute window, which makes it much more efficient. So similar things can be done with transformWithState. And not just that, there's even more functionality. Whatever I have discussed so far is all in open source, but there is this brand new functionality that we are working on, like ability to express TTL on the state store. You can initialize the state from an old query or from a different query into the new query, such that, for example, let's say you're trying to modify your query, but you want to test it. Before you go push that to production, you can actually initialize your test query from the production state, and then if you're happy with it, you can push the query. And the big thing that we are going to support is schema evolution. This is the biggest pain point that we heard from customers today, where if once you have state created, that schema cannot be evolved. It would involve you to delete that entire state and reprocess the data. We would be allowing for things like additive schema, like our type widening. These things would be allowed with the state store. All of this is going to be in public preview in Q3 of 2024. Python will also be supported. But if you want to try it out, you can do so with the Scala API in open source. With this, so far we have discussed what we have done and what are some of the near-term features that we are going to launch. But there's a lot more coming, and we are listening to our customers and a lot of things that are in the pipeline that we are thinking about. These could be in the performance spectrum. It is in the functionality. Like state is something that we really want to bring in as a first-class citizen into the structure streaming API, support like things like state repartitioning, ability to do CRUD APIs against the state, so that you can build a lot of sophisticated applications. And again, why is state a big focus for us? The reason is when you're building real-time applications, you don't want to leave the engine to go to an external layer. You want to do all of this within the engine for the performance. This state becomes like really critical. complex event processing, adding functionalities to DLT, and then connectors. These are some of the sessions. There are some sessions that were done yesterday or earlier in the day, but there are some sessions coming up around streaming. If you're interested, please do check them out. With that, I thank you so much for coming and listening to us, and I hope you're as excited about streaming as me and Ryan are.